That's lovely. So welcome everyone to this lovely public talk. Perhaps you can it. Yeah. So today it's a pleasure to introduce Dr. Justin Dressel. He is an associate professor, associate program director for the Faculty of Physics, and co-program director of physics here at Institute. It's on your website. Yeah. So here at Schmidt College of Science and Technology, here at the IQS, the Institute for Quantity Studies. So he did his master's at the University of Rochester and PhD at the University of Rochester, right? And his research is primarily focused on quantum information science, quantum computation, and the foundations of quantum physics. And according to him, these fields are the natural intersection points between physics, maths, and computer science. And today, Justin's here to this lovely public lecture to talk about understanding the 2025 Nobel Prize in Physics.
Thank you, Chris. So thank you all for being here, and I especially thank the organizers for encouraging me to give this public talk. As you'll see shortly, the reason I was asked to give a public talk about this is because the prize is right in my wheelhouse of what I do a whole lot of research in. And so I'm kind of a natural choice to tell everyone about what this prize means, why it's important, and hopefully you understand some physics along the way. I'm targeting this talk to be a very, very broad audience, so I'm assuming nobody knows anything. So you're in good company if you feel like you know nothing, and we can start from scratch. So first of all, what is the Nobel Prize in 2025 for physics? Well, according to their website, it was awarded to these three gentlemen, John Clark, Michel H. Devoret, and John M. Martinez. The website says the Nobel Prize in Physics 2025 was awarded jointly to John Clark, Michel H. Devoret, and John M. Martinez for the discovery of macroscopic quantum mechanical tunneling and energy quantization in an electric circuit. This is very succinct, very clear. If you already know what this is talking about, you just say, oh, okay, I understand. They definitely deserve this prize. If you don't know what any of these things are, let's go through them one by one. So the first thing here is macroscopic quantum mechanical tunneling. So let's unpack that a bit and say, what is this? So what is quantum tunneling? And why is macroscopic quantum tunneling such a big deal that it merits a Nobel Prize? Well, at macroscopic scales, objects bounce off barriers. This is not a very surprising phenomenon. We do this every day. What's more surprising, or it would be more surprising, if you tried to throw an object at a barrier and it just sort of suddenly passed through the barrier and appeared on the other side. This is what's called tunneling through a barrier. And classically, at macroscopic scales of everyday life, we don't see such tunneling. We don't expect to see such tunneling. It'd be very weird if such tunneling were to occur. However, small objects behave differently in the quantum domain. And a simple example of this is that if I look at particles in the nucleus of an unstable atom, they're bound together with an energy barrier that they can't escape. So you can think of this as kind of throwing a ball against the wall. The particles in the nucleus kind of can't get past this barrier of energy inside the nucleus. Now, classically, this would mean they'd be forever stuck. However, occasionally, for these unstable atoms, particles can tunnel through that energy barrier and emit on the other side of the barrier particles, like these alpha particles, for example, which is a source of what's called nuclear radiation. So alpha particles get emitted from unstable atoms as nuclear radiation because of this tunneling process. They tunnel through the nuclear energy potential barrier and appear on the other side, which means they escape those atoms and come straight out and then hit other things. That's one example. We actually use this phenomenon of quantum tunneling all the time in technology these days. It's very well established in the quantum domain. An example of this is the scanning tunneling microscope, or STM, which actually itself got the Nobel Prize in Physics in 1986. So what is
for an object?
For making this thing, yes.
The one that made the object, not for the object itself.
Yeah, but for making this particular object. Indeed. So what does this scanning tunneling microscope look like? Well, it's a device that has a very, very thin electronic tip kind of goes down to a needle. You put this needle very, very close to something that you want to image, like a sample of some sort, and the electrons on the sample will tunnel across this air barrier, and which is a gap, into the STM tip. And then you can use that little microscopic current of those electrons that tunnel across that barrier to image the microscopic structure. And this has allowed us to get images down into the nanometer type scale of various objects. This kind of image wouldn't be possible with light because light's wavelengths are far too long. So in fact, being able to use electrons, which are much, much smaller objects, and this tunneling kind of behavior at the tip allows us to very carefully kind of map out microscopic details. This is an extremely useful thing, this tunneling microscope. But the important thing to note here is that classical objects would require more energy to enter the tip of such a microscope because there's a potential energy barrier between the sample and the microscope tip, in this case the air gap, and a classical particle wouldn't be able to get over this energy barrier. It would need to be given some energy by something else in order to get over the barrier and get into the tip. But because electrons are quantum mechanical, what's happening here is that they're tunneling through the barrier and get them leaking through in this kind of exponentially damped way with increasing distance. And if that tail, that exponential tail, gets all the way to the other side, then there's a probability that it can just jump over to the other side and appear there, and then suddenly be in the microscope tip and contribute to your images. This is a very strange behavior, but one of the cornerstone behaviors of quantum mechanics that makes it very different from the way our macroscopic classical world behaves. So this leads us to a big question, which is how big does an object have to get before it can't tunnel anymore? Because we see examples of these microscopic objects, these quantum mechanical objects that can somehow leak through these barriers with low probability, but they can still somehow appear on the other side, whereas a classical object doesn't. A macroscopic object like a ball doesn't seem to do this. If I go run into that door, I'm unlikely to appear on the other side of the door. I'm far more likely to embarrass myself. And I'm pretty confident that I'll embarrass myself. So clearly I am macroscopic in this sense that I don't tunnel through barriers typically. But this raises a question of what constitutes tunneling through barriers? Like what makes it macroscopic or not? Basically, if you have a situation like this, if there's a lion on the other side of the barrier, you want to be pretty confident that it's not going to tunnel through the barrier and somehow cause you a bad day. So it's kind of an important division to place between this macroscopic world where we don't see tunneling, and this microscopic world where we do see tunneling. And interestingly, when we've tried to draw this division in physics, we run into a lot of problems. There doesn't seem to be anything in our physical models that tells us when something is macroscopic or not, other than we just observe it behaving macroscopically, as in we don't see these quantum effects, we don't see this tunneling. So there's a question here of, is there a size limit to what quantum mechanics can describe? Is it secret just we make it big enough? Is it enough mass? Is it enough things moving together? What is it that distinguishes the microscopic from the macroscopic in a better way? Do these big objects behave fundamentally differently than these tiny objects? Or are these big objects actually still quantum mechanical kind of all the way down and can still do strange things like tunnel if you arrange the right circumstances?
Only a question of size is not the question of the chemical composition.
Well, this is the question. It's like, what about it makes it macroscopic? Is it just the amount of mass, or is it something else? Is it something about the arrangement of charges that makes it different? Is it something about the length scales that makes it different? Is it something about the number of objects? If I have 10 to the 27 objects all bouncing around, does that make it macroscopic? It's not clear. And I'd say there's been a lot of research over the years trying to better draw this boundary, the division between what is quantum, what is non-quantum, as you increase various scales on various things. So tunneling is one of these criteria that we can use, a very practical criteria. If it tunnels, then it's quantum mechanical, because a classical thing is not going to tunnel through an energy barrier. This is pretty clear evidence that we have quantum behavior of whatever that object is that did the tunneling. So we can use this as a criterion.
The Leon is not quantum.
So what is not?
Leon is not quantum.
Yeah, typically we wouldn't consider a lion to be quantum because we haven't observed it tunneling through a barrier, or at least anyone who hasn't survived. So there might be some survivorship bias to our data. We have to be careful here. This brings us back to our Nobel Prize again, and let's keep going with our phrasing here. So now we have a rough idea of what this macroscopic quantum mechanical tunneling is and why it would be really important to see. The second thing here is energy quantization in an electric circuit. So what does this mean? So what is energy quantization in an electric circuit? Why is it such a big deal? Well, if we look at classically bound systems, an example here, it would be a planetary system where you have something like a sun at some focus of an ellipse and some planet that's orbiting around the sun. The planet is bound to the sun using this gravitational force, for example, which means it is confined to a fixed distance away from the sun. It can't get arbitrarily far away. It's always kind of close to the sun. This is what bound means. And it creates what's called an orbit around the sun in this kind of ellipsoidal configuration. So classically bound systems have motion that's determined by some sort of potential energy of this confining force, like gravity. And if we were to look at the effective potential energy for such a bound orbit, we'd see a structure that looks something like this blue curve, where you have a well in it. It sort of dips down and then comes back up. And the idea is that if you're in such a bound orbit, then your energy of your motion is inside of one of these wells where you end up seeing two barriers. So if you draw a horizontal line here of your energy, you're going to intersect your potential energy curve in two places, which means you have two barriers, and you're just going to oscillate between these two barriers because you can't escape those two barriers. This is what bound means. In this kind of situation, what the parameter is here horizontally is the radius away from one of the bodies. And so as you move along the ellipse, you'll get closer to the body until you reach some minimum radius. Then you'll keep moving along the ellipse and move further away from the body until you get some maximum radius, and you'll just go between this minimum and maximum. Now, the specific orbit that you are allowed to have depends on the total energy of your motion, because the energy is in general conserved as you're moving around such a bound orbit. And so as I change the energy, this is like moving up and down in this plot, I'm going to change where I hit the intersections on this curve, which will change kind of the minimum and maximum radii of the orbit. And I can even go all the way down here, and you'll notice there's actually a minimum where I hit like kind of minimum point of this potential energy where it's at a single radius. That would correspond to a circular orbit. So if I had a perfectly circular orbit around the sun, I'd have a minimum energy orbit. All the other orbits around the sun have higher energy than that and create ellipses. And then if I create an energy that's high enough, eventually I can go over the potential barrier and then I can escape. And this is what happens with things like asteroids or stuff that kind of go close to the sun and then keep going forever in this kind of hyperbolic path that goes off to infinity, just escapes and leaves. So that's what we mean by a bound orbit or a bound system. And what's important is that classically we're allowed to have any of these energies. So I can draw any of these horizontal lines in this graph, and that tells me kind of which orbit I end up on, that orbit with that particular energy. But there's no constraint about which energies I can have. Now, when I start looking at small bound objects like atoms, they behave differently. So for example, a hydrogen atom has a very similar structure to like planetary system like sun and planet, where I have a charge, a positive charge, a proton in the center, and a much lighter electron that is negatively charged further out. It's attracted to this positive charge just like a planet is attracted to the sun with gravity. In fact, the math looks basically identical between these two cases. But unlike planets orbiting the sun, when we start looking in detail at what can happen with such an atom, we find that only very particular energy levels are allowed for such a bound system. Now, once it's unbound, this is no longer true. We can get like any energy we want. But as soon as we get a bound system where it remains confined near this kind of positive charge, this electron remains confined, what we find is that the energies discretize. This is what we mean by quantization in quantum mechanics, and it means that only specific energies are allowed. Every other energy is forbidden. And you can think of this in the sense that if you tried to have one of these other energies, it would be fundamentally unstable, and so you'd end up relaxing to one of the stable energetic configurations, allowed energy configurations. And this is quite surprising because, well, first of all, it's very convenient for us in terms of our existence, because if atoms didn't have this property, then there would be no limit for this electron, for example, collapsing all the way down into the center of this atom. Instead, what we find is there is actually a minimum energy known as the ground energy, ground state energy of such a configuration that it can't go below. And because it can't go below, it means I'm always going to be confined with some kind of minimum radius, and the atom can't get any smaller than that. It can't collapse in on itself. This is nice because if that weren't true, all our matter might be fundamentally unstable. We might collapse entirely. All of the atoms in our body could collapse down to points. But because of this minimum energy that's allowed in a bound system, we don't collapse. And moreover, we don't lose any energy from anything else. It can only occupy this energy, so it sort of just stays there in some stable configuration. Now, the other thing to note is that there are big gaps in energy between the allowed energies. And that means that I can't just kind of perturbatively move the energy up and down from something. I have to get a big chunk of energy from somewhere, a big discrete chunk of energy. Otherwise, I'm not able to kind of move my energy around. You can think of this as kind of like a stepping ladder, if you like. I can stand on one of the rungs of a ladder, and I'm there. This is my stable energetic configuration. But if I want to climb up one rung or go down one rung, this requires me to do something. I have to either gain a fixed amount of energy to go up one rung of the ladder or lose a fixed amount of energy to go down one rung on this ladder. And the atoms have this kind of structure of these different allowed rungs of the ladder, which then correspond to different radii of these bound orbits, which means I'm going to get different radii of orbits, very crudely, of my atom. These are now known as the Bohr orbits. And if you take a chemistry class, you know these very well as the atomic shells. If you think about like the S shell, the P shell, the D shell of an atom, as you learn in chemistry class, these are precisely those shells. So energy quantization in quantum mechanics is this phenomenon where any bound system that I have, where I have a potential energy that has a dip in it, that has a minimum, and you can be confined between kind of two sides of this well somehow, you're going to get this quantization where I have only fixed allowed energies. I won't be able to get any allowed energy inside of that well. Now, this phenomenon has led to all sorts of interesting technology quantum mechanically. So for example, photons are packets of light that have specific amounts of energy that are indicated by the color of that light. And so what that means is that if I have an atom, like a hydrogen atom, and it needs to jump between different energy levels, meaning these different kind of radii of the atom, then what it can do is it can either absorb or it can emit this packet of energy in the form of a photon. And the amount of energy that it needs in order to get from, say, n equals 1 to n equals 2 of these energy levels will determine what color of photon I need to absorb or emit. Now, this is very interesting because each atom has kind of a different energy level structure, which means the transitions between the different energies are different for each atom. And that means we can use the specific colors that are either absorbed or emitted as these photons as a fingerprint to identify kind of which atom we're talking about. This is a whole field known as spectroscopy, and you see this being used all the time throughout all the sciences now. where if we want to know what is the material composition of something, we'll often just put it in a chamber, light it on fire, make it some gas, send some light through this gas, and see, oh, how much of it gets absorbed or how much of it gets emitted on which spectral lines. And what that means is we're going to get either bright or dark lines depending on where these specific energy transitions are in the atomic structure of the material. So this is extremely robust and important phenomenon that only quantum mechanical systems show. This discreteness of the energy levels and this the specificity of the energy packets required to make the system do something. Like I have to give it exactly the right amount of energy, otherwise nothing happens. So far, so good? Well, electronic circuits, coming back to topic at hand, can also have this kind of notion of a bound state. So a simple example of this would be an LC oscillator, which you see here, where I have charge that initially starts, say, on one side of a capacitor, and it flows down this wire through this inductor and ends up on the other side of the capacitor, and then kind of reverses course and repeats itself. So you get charge that's now oscillating back and forth between two different capacitive plates in my circuit. Oscillation I can describe using a potential energy function like so. It'll look parabolic like this because it's a nice simple harmonic motion, which means that once I fix the energy in such a circuit, what I'll see is something like the magnetic flux in the inductor will move up like so, and then move back to zero, and then move back over here, and then it'll just oscillate between these two bound points, just like a planetary orbit will like oscillate between two different radii as I have a fixed energy. So these macroscopic electronic circuits, we use this kind of circuit all the time. This is actually known as a tank circuit in electrical engineering. This is used to create clocks where things are oscillating at a very nice, regular motion. So we use these all the time. But whenever we use these electronic circuits, they seem like macroscopic objects. They have a nice potential energy structure, and I seem to be able to have any of the energies allowed inside of this bound configuration. Even though I have a well here, a potential energy well, this means I have a bound system. I'm seemingly able to have any energy in that bound system. So the point is that if such an electronic circuit were to behave quantum mechanically, then what we'd expect is that should it get these discrete quantized energies instead, because it's a bound system. We wouldn't be able to have just any old energy in this oscillator. We'd only be allowed to have these specific discrete energies. And we could even count them going up. We could quantify what the energy packet is between each of the energy levels, and we can go up. So the big question is, like, why don't we see these quantized energies normally in electronic circuits? And we can approach this question from two different angles, right? One is that this is a macroscopic circuit, so why would we even expect it to be quantized? We should see just a classical circuit. Then there's no surprise. But I could also say these are electrons we're talking about, electrons moving around in the circuit. And we just learned from our atomic structure that electrons, these same electrons, when bound by an atom, do exhibit discrete energy levels. So and then there's a question here, like, okay, we have a fundamentally quantum object, like an electron, which we know can produce discrete energy levels in an atom. But now if I put it in a circuit, it doesn't seem to have such discreteness. So why not? Why don't we see discreteness of these electrons in these circuits? Well, to analyze this, we have to understand what's going on with these circuits. Like, what is in the wire itself? Like, where are these electrons? Well, these electrons are made of conducting metal. And at normal temperatures, there are millions of these charges, billions of these charges, huge numbers of these charges moving around in this metal. And they're all kind of bumping into each other randomly in a disordered way. You can think about them as just a sea of people all kind of jostling each other and exchanging energy with each other. This is a very kind of chaotic, if you like, type of motion. And it is in some sense no surprise that that kind of degree of disorder might average out some of these subtler behaviors quantum mechanically. So this disordered behavior of the electrons when they're in this kind of fermionic state, and I'll get back to this distinction in a second. What it does practically is it causes resistance in the wire. So basically, as these electrons bump into each other and rattle about, this generally heats up the whole lattice of the positive ions that are confining all of these electrons to the wire. This means the lattice itself starts jiggling, and you see this lattice jiggling as heat of the wire. And this means that some of the motion of the electrons, the energy of that motion is being lost to the motion of the ions in the lattice of the wire. The other thing that happens is that all of the energies that these electrons have, they're all doing different things. They're all having slightly different energy exchanges. And all of that gets averaged out over this very, very large ensemble of 10 to the whatever number of electrons that are in this wire. And that averaging process kind of erases any of the discretization that I would have seen in these bound potentials. It sort of fills in all the gaps, if you like. And so I'm just unable to see much. But this means that we have an idea then of if we're going to see any such quantum behavior in such a circuit, what we need to do is cool it to a low temperature. And what this is going to do is reduce that jiggling motion so that we get much smaller energy fluctuations. And that means we're going to be averaging many, many, many smaller kind of jiggling motions together. And we want to prevent these electrons from kind of bumping into each other in the first place, because that's just complicating everything. If we can make all the charges move together without fighting each other, then we might have a chance of being able to see the intrinsic quantum behavior of these electrons. But as it stands in normal temperatures, normal room temperature, normal conductors, all of these effects kind of conspire to prevent us from seeing all these things. So, and this is where kind of it's leading closer and closer to our Nobel Prize. What did these researchers do? Well, they were studying a phenomenon known as superconductivity. And this is what led to this idea. And superconductivity is the observation that if I take a metal and certain conducting metals, materials more generally, and I just cool down their temperature and cool it lower and lower and lower, then what you find with a normal metal is I can cool that temperature lower and lower, and its resistivity will lower as well, because you get less jostling motion, which means it's bumping into each other less, which means you get less heating and less resistance. But for a normal metal, you kind of saturate to finite resistivity. You can cool it down as far as you want, and you still can't get rid of all that resistance. But there are certain metals and certain materials where I do the same thing. I cool it down and cool it down and cool it down. And then there's a sudden critical temperature where something changes. And the material organizes itself and suddenly drops to zero resistance. And this means that all of the electrons that were moving in that material now are no longer fighting each other. Somehow they're no longer causing heat. They're no longer having all their motion get absorbed by that like positive lattice. They all are just flowing kind of smoothly without any issues. Now, under scrutiny, trying to understand this behavior, the way we are currently understanding it is that the electrons end up pairing up with each other, and they start moving together in a cooperative fashion. Now, more technically speaking, what this means is that electrons, which are fermions, meaning these are kind of very individualistic particles in the quantum world, by pairing up with another fermion, two fermions kind of become equivalent to a single, what's known as a boson. And a boson is a type of particle that likes doing the same thing as other bosons. It's a much more cooperative, collective entity rather than an individualistic entity like a fermion. So it's very interesting that this is even possible, that you can take two very individualistic objects like electrons and basically join them together so that they start behaving like a pair. And this pair now starts behaving collectively. Now, the net effect of this is this pairing mechanism, and we're still researching kind of the details of how this pairing mechanism happens. What this pairing mechanism allows is for all of these Cooper pairs to kind of move in unison, move together, stop colliding with each other, stop losing energy to the lattice, which is why the resistance goes to zero. But what's important here is even though I've dropped the temperature and therefore dropped the resistance to zero in such a superconducting circuit, there's still a macroscopic number of these bosonic Cooper pairs flowing through the wire. So I haven't changed the number of electrons flowing. There's still an enormous number of them. And macroscopic is no exaggeration. We're on the order of kind of number of atoms and what I would typically think of as a macroscopic object. But now this macroscopic number of objects, these pairs, are behaving in an organized way. They're all moving together. They're not fighting each other, not colliding. And in fact, under even more scrutiny, what you find is that these Cooper pairs will actually condense into a single cooperative entity. And this entity is known as a Bose-Einstein condensate. And it behaves as basically one macroscopic quantum object. And this is truly astonishing that this happens. We have, again, millions of these things all together, but we can describe them with a single quantum state as if they were a single quantum object. And that quantum object kind of moves all together. There's no distinction between any of its parts any longer. It is just one conglomerate entity. I guess if you're like politics, this will be the ultimate goal of something like communism. Everyone moves all together and there is no individuality any longer. But nature does this kind of automatically at these really, really low temperature scales. We get these macroscopic quantum objects described by a single macroscopic quantum state. Very strange, but it raises an interesting question. And this is the question that John Clark was raising, and he was building off the work of Tony Leggett as well, who also asked this question around this time, which is, can these superconducting circuits allow us to see this fundamentally quantum behavior of these macroscopic collections of charges? Or are they simply so big that macroscopic means macroscopic and it washes out all the quantum behavior? This is now a clear experimental test, because this whole story about superconductors and how all these things pair up and these macroscopic states and all that, that was all theory in order to explain why this resistance went to zero. This is saying this is what we expect quantum mechanically to have happen, but it wasn't necessarily experimentally valid. There's a lot of theory there. You can just do a lot of math. It seems plausible. You go into the lab and you discover, oh, this math is nonsense. So the question is this nice story about this Cooper pairs, this macroscopic Bose-Einstein condensate and so forth, is this actually the way it works? Or are we going to run into some macroscopic limit where now we're too big, our size is too big, and we're going to see macroscopic behavior and won't tunnel, won't do other things? So we can now ask very specific questions. If we create such a macroscopic collection of charges in such a supercooled circuit, will they tunnel through barriers, that collection of charges? If they can tunnel, that's a pretty clear signature of quantum mechanical behavior. Do they have quantized energy levels? If they do, that's also a pretty clear signature of quantum mechanical behavior, meaning it's a bound system. It should have discrete quantized energy levels, and we can check that experimentally. So this is what these guys were doing. So coming back to this Nobel Prize, we can now read this whole statement. What was this awarded for? It was for the discovery of macroscopic quantum mechanical tunneling and energy quantization in an electronic circuit. So this kind of tells us immediately that indeed we do see quantum mechanical behavior here, even though we have a macroscopic collection of charges. And thanks to their hard work, we know that these macroscopic collections of charges indeed tunnel through barriers, and they have quantized energies, exactly as we'd expect quantum mechanically, even though they're macroscopic. And what's really important about this is that this work has laid the foundation for an entire industry that uses the quantum features of these superconducting circuits to do things, because this gives us a way to engineer systems that manipulate quantum mechanical behavior in a controllable way, which is kind of a big deal. So let's go back a little bit and see what did they actually do that the award was given for. So at the time this was done, John Clark was a PI, so he was a professor at UC Berkeley. And he had in his group Michel Devoret as a postdoc and John Martinez as a graduate student. John Clark, he joined UC Berkeley in 1969 and had established himself as a leading experimental researcher for such superconducting circuitry. and had done a number of groundbreaking experiments already. But between the years of 1984 and 1985, he specifically worked with these other two gentlemen in his group on three groundbreaking experiments that led to this Nobel Prize. And the experiments tested the new type of circuit element that is known as a superconducting tunnel junction, or now is called a Josephson junction. And that allowed them to actually test the predictions about whether this behavior really was quantum mechanical in the way that we expected it to be. So this, of course, raises the question, what the hell is a Josephson junction? So what is that? It's actually much less scary than it sounds. It's just a thin insulating barrier placed between two superconducting wires. So here's actually an image of one that was taken a couple years back at UC Berkeley by some collaborators of mine. And you can see some aluminum wiring here. And then in between them is actually a little aluminum oxide layer that's insulating. And then there's another aluminum wire underneath. Now, aluminum, when you cool it down, becomes superconducting. But aluminum oxide does not. It maintains its insulation characteristic. So this means now I have two different superconducting wires that are separated from each other by this insulating barrier. And you can think of this as a tunnel barrier, where now stuff from one superconductor can tunnel across this barrier to the other superconductor, but it won't flow classically because it's actually a barrier classically. So commonly, even in modern circuits, these wires are still aluminum. The barrier is usually aluminum oxide. And you get this kind of what's called a heterostructure that has superconducting materials, wafer or sandwiching this little thin tunnel barrier. Now, what's important here is we get two distinct kind of conglomerates, one on each wire, which are superconducting. They have their own macroscopic superconducting state, but those states now have to talk to each other by tunneling across this barrier. And so you get some very interesting behavior out of this. Now, when we map out kind of what is the potential energy of this barrier, it actually versus something like magnetic flux in the circuit, for example, then it actually has a cosine-like potential, like you see here on the top, which is a very interesting shape of potential for such an element. And what this means is as I change the flux through this junction, then I can move back and forth along this cosine. And you see a cosine is basically a series of wells. So I can just be trapped in one of these wells or the next well over or the next well over and so forth. But if I get too much energy, then I can actually get above the height of the cosine and escape this cosine. So it actually has bound behavior below this cosine well, and unbound behavior as I get too high. Now, what's also interesting about such a junction is if I just place a voltage bias across the junction, then what this ends up doing to this potential is it tilts it, and it ends up looking like a washboard. So I get this cosine that's kind of tilted downward, and then I end up with a washboard-like structure, which means I can isolate kind of one of these wells at a particular energy, and one side of the washboard will look like I can kind of tunnel through it to the other side, while the other side of the washboard now has this very big barrier I can't get through. So it's a very nice structure for being able to kind of isolate these kind of bound types of behavior in these circuits, which is why they were looking at such a Josephson junction to do these experiments. Now, if the charges, as we predict, remain quantum, then these collections of charges should show, first of all, quantized bound states inside the washboard, which means if I tilt my washboard potential just right so that I kind of have a little dip in it like this, then that is a bound dip, which means I should end up with discrete energy levels inside of that dip. The other thing I should see is tunneling through the barriers if it's quantum mechanical, meaning that if I'm in such a bound dip and I still have a potential barrier that's higher than this dip, then I should have some probability of just appearing on the other side of that barrier, tunneling out of it and escaping and going off somewhere else. Now, in this case, what going off somewhere else means is I get an electron that kind of gets across this barrier and then can make it to the other side and contribute to some measurable current in my signal. So what I can actually do is just measure kind of what is the current across one of these junctions. And then by looking at what is the collected current, as I vary some things, I will be able to see, does it have this structure or does it not have this structure? So more practically, What this means is that if I lower the temperature of such a thing, it should decrease the energy fluctuations because temperature is just everything jiggling around. That jiggling around can cause jumps that allows it to kind of go over the barrier just by getting extra energy from something else that was jiggling. So by lowering the temperature, I reduce the amount of jiggling. At some point, I'm going to lower the temperature fluctuations to below the height of the barrier, in which case I can no longer use the temperature fluctuations to get over the barrier. The only way I can get across the barrier is by tunneling if I do that. So by lowering the temperature, then I should be able to see a transition between what looks like temperature activated jumping over the barrier and tunneling through the barrier. They should look different. The other thing I should be able to do is tilt the bias, which is just changing the voltage across this thing, which will tilt the washboard and make the tunneling rates out of particular energy levels controllable. Because if I tilt it differently, what I'm doing is I'm changing the position of where the height of this barrier is. I'm kind of lowering it if I tilt it more. And what that does is it places the height of this barrier near different energy levels. So you can see if I can just tilt this downward, I'm first going to hit this energy level. And if I keep tilting, I'm going to hit that energy level. And if I keep tilting, I'm going to hit that energy level. So what I should see if I tilt my washboard potential slowly is that there should be discrete jumps where I get sudden increase in kind of current through it, and then a decrease, and then a sudden increase in current, and then a decrease, and then a sudden increase and a decrease. So if I see spikes in the current at discrete intervals, as I keep tilting this washboard, that's a clear signature of the discreteness of these energy levels inside that washboard. So what did they see? So John Clark went with Michel Devereux, John Martinez, and did these experiments on these Josephson junctions. And here's an example of evidence of tunneling. So if he lowers the temperature, so he starts at say 1,000 millikelvin, gets some particular escape rate from one of these things, meaning you're like tunneling across, you're getting a current across this junction, and you lower the temperature steadily, what you see is a linear dependence on this temperature with this tunneling rate. And that's a clear indication that this tunneling rate or this escape rate is caused by thermal activations. As I lower the temperature, then I get in direct proportion to my lowering the temperature, this decrease in the escape rate. Now, if I keep lowering the temperature, then what I'd expect for a classical junction, and here they actually experimentally modeled a classical junction by introducing an external magnetic field to kind of prevent prevent the tunneling, essentially. So they found a way to prevent the quantum mechanical tunneling effect, but keep the thermal jump effect. For such a classical junction, they do continue seeing this linear dependence as they decrease the temperature. But if they turn off this extra mechanism and just look at the raw junction, then as they decrease this temperature, they see a plateau appear here. That temperature goes down, but the tunneling rate, the escape rate, does not. So what this means is that even though my temperature is going further and further closer to zero, my random fluctuations that could be giving me energy to get over the barrier keep decreasing, and I'm not changing the barrier height. Even though temperature is going down, I still get this consistent rate of jumping through the barrier, tunneling to the other side of the barrier. So this is consistent, this kind of saturation behavior is consistent with quantum mechanical tunneling, that somehow current can get across the junction even though I don't have any thermal fluctuations available to kind of get over the barrier. It just kind of gets through the barrier anyway. So this was a clear signature of the quantum tunneling that they expected to see. That was in this nice paper here. This measurement of macroscopic quantum tunneling out of a zero voltage state of a current biased Josephson junction. And now you understand all those words, so you know I'm not lying to you. The other thing they showed is evidence of energy quantization. And so the way they did this is by fixing a particular low temperature. And then they looked at the rate of the charge flow through the barrier as a function of the bias, which again is tilting this washboard potential. And so as they kept tilting this potential, then indeed what you expect to see is that as you tilt it further and further, you're going to have this barrier on one side kind of lower and lower and lower. So you're going to first hit one energy level, and then you're going to hit the next energy level, and then you're going to hit the next energy level, and these kind of spikes. And you look at the data they have here, and indeed you see these very distinct spikes in current as you tilt this washboard potential so that you see these are very well-defined energies that are trapped inside of this little well inside the washboard potential. So energy quantization can explain these peaks in the data, and they exactly conform to what we expected to see from quantum mechanics. And this graph is from another one of their papers, is energy level quantization in the zero voltage state of a current biased Josephson junction. So short answer is yes, they did find that even though we have a macroscopic number of charges in this system, they were all behaving collectively in a way that allows them to preserve that quantum mechanical behavior. They weren't fighting each other anymore. Everything was going smoothly. They behaved like one giant macroscopic quantum mechanical state with all that comes along with that, including tunneling, including energy quantization, and so forth. Now, what's happened since then? Well, John Clark still is at UCB, Berkeley, doing great experiments. He's influenced generations of people at this point, truly phenomenal researcher. Michel Devoret ended up at Yale for many years, running a superconducting quantum circuits type group there. He recently has moved to UCSB, so now he's also part of the UC system here on the West Coast. John Martinez worked at NIST for quite some time and then moved to UCSB for quite some time. Where I first met him was actually on a joint grant with him while he was at UCSB. Wonderful person. Then he joined Google. Google actually bought out his entire lab and said, this looks really important. Let's add this to one of our Google Moonshot programs. And then he got fed up with corporate life in Google, so he left Google. But now he started his own company, QuoLab. So I guess is still pushing a lot of these things forward. A lot of very influential people. All three of them have just influenced generations of researchers and wildly influenced all of this, all of these things. So as I state here, the breakthrough has enabled an entire industry of using superconducting circuits to engineer custom macroscopic behavior or custom quantum behavior at the macroscopic scale. And this is something that you have to kind of pause to understand how important that is, that we can customize quantum behavior in an engineering sense at a macroscopic scale where we can fabricate devices. Because too microscopic, it gets hard to fabricate things, but if it's macroscopic enough, it's much easier to control. So their work has enabled us to do that. In particular, these artificial atoms that we can build using such a circuit have enabled one of the most promising avenues for building what's called a quantum computer, which is actually what I research. And I use these superconducting circuits to do that. So as a quick example here of what I mean by artificial atoms, we can take some of these potentials that we make some circuits, and we can make them look very similar to atoms with exotic properties. So for example, an actual atom has a potential structure that looks like this with discrete energy levels that appears in it, just like the hydrogen atom we saw earlier. If I sculpt electronically a different kind of potential well, like this quantum dot, I'm going to see a similar discretization of allowed energies, just like an atom. Or if I use one of these Josephson junctions, as we just saw, I can get the same thing. This means that I get bound states of something with discrete energy levels, just like atomic configurations. But now I can engineer kind of what the spacings of these energies are. I can engineer kind of how big they are in the chip. I can engineer how do I talk to these atoms? How do they couple to the external environment? These are things that are very difficult to do with actual atoms, but now become very easy to do with these engineered artificial atoms. Now, this has led to something called quantum computing. And I always like showing this image because this is what like ChatGPT tells me quantum computing is. I have no idea what this is, but this is apparently what the overall like media hype thinks of quantum computing. So what is an actual quantum computer? You'll often see images like this as well, which looks beautiful, this kind of chandelier-like object, all of solid gold. And anyone who's worked in one of these superconducting labs will tell you you're looking at a refrigerator. That is not actually the quantum computer. That's just the thing that cools down your quantum computer. And in fact, it should go inside a big kind of cylindrical case. Otherwise, it doesn't cool very much. So the thing when it's actually running doesn't look quite so nice. But very briefly, the idea behind such a quantum computer is that computation is fundamentally a physical thing. You're transforming information from one form to another. We have a whole theory of computation built on machines called Turing machines, which are physical machines that do this kind of transformation. But when computation was created by Turing and others, they were thinking about classical physics. And so they made a classical machine as this Turing machine. But we know that the physical world is actually better described by quantum physics, like these atoms, molecules, and now superconducting circuits. They don't generally behave like Turing machines. And so the question is, does quantum physics actually change the possibilities of this computational model? The answer is yes. Because quantum physics extends classical physics, the theory of computation, classical computation, extends to bigger theory of quantum computation. And that's a lot of what I do. But superconducting quantum computation is a big enterprise now toward that goal. It's one of several. There's also ion traps, there's neutral atoms, there's semiconducting platforms, and so forth. But superconducting quantum computation is a big, kind of fairly successful industry right now. We use these artificial atoms. We can build whole chips like you see here from UC Berkeley of multiple interacting artificial atoms that we can control with various wires and microwave fields and so forth. Now, companies have gotten on board with this. For example, I mentioned that Google bought out John Martinez's group at UCSB. So here's John Martinez himself with his UCSB crew when they got bought out by Google and the sorts of chips they're building at Google before John Martinez left again and left them to continue his work. IBM also got on board with superconducting qubits. So here's Jake Mbeda and a few other people at IBM. There's other small companies like Rigetti Computing that are also building superconducting qubits. So here's a few years ago, they had a nice processor. And IBM is trying to even build big quantum computers by building a big one of these fridges. So this is an example of their GoldenEye project, where they actually have a huge dilution refrigerator in order to fit even more quantum computing stuff in it. So there's a lot going on, way more than I can talk about right now. But I'll stop and just issue a heartfelt congratulations to these Physics Nobel Prize recipients in 2025, because they certainly deserve it for their impact that they have had and will continue to have on physics as a whole, but also industry, quantum computing, and the engineering sector. So thank you.
I think we have time for questions. So either from here or from the online audience. So what are your questions?
So, not a very theoretical question, but
the little that I understand make me think that there is a lot of experimental work behind that. And you said at the beginning that is very close to your work, also to the work that is made here in the Quantum Institute of Chapman. But how do you, where do you do this experimental work? Because in Chapman, I don't see any experimental superstructure that allow you to do it. So how is possible to do something like that at Chapman?
Great question. Yes, you notice this requires these big dilution refrigerators, rooms full of equipment and so forth, and we don't seem to have any of that kind of equipment here at Chapman. We do have other experimental labs now as of the renovation of this particular building, but they're all quantum optics type labs. However, Armin Goulian does have a superconducting laboratory on the second floor of the experimental building over there. His focus is not so much on these particular aspects of superconductivity. He's looking at kind of higher temperature superconductivity, really exploring different mechanisms for making superconductivity and so forth. So he does have some of that. What I do, however, since it's more focused on quantum computing, is I collaborate with other experimental teams that aren't local. So right now I've had a long-standing joint grant with Irfan Siddiqui at UC Berkeley, for example. He has an in-house fabrication facility at UC Berkeley. He can make his own chips there. And I work very closely with his experimental team to both design and test various like superconducting processors, various components in those processors, how those processor components interact. We have to model those, tell them how that's going to behave, then they can test it and say, does our model work? Or do we need to go back to the drawing board and actually like redo our modeling?
so it would be a good politic to try to convince our provost to invest money in this sort of experiment for making a chap in a place where this is possible?
All I can say is we have established experience in that sector. So the more people who are here to be able to do that, the merrier. Space is always a concern. So how that fits out with priorities on various aspects of research is always a question. But certainly I'm happy to keep collaborating. And like I mentioned, I'd collaborated also with John Martinez for some years. Wonderful person. He has done several experiments I proposed in his laboratory, both before and after he was at Google. So I've had good working relationships with these people. Michel Devereux, I interact with several times a year at various conferences. He's a wonderful, wonderful man who knows a lot. I learn a lot from him every time I meet him. So it's been a pleasure of mine to have intersected with these characters. And I even met John Clark visiting UC Berkeley, though I haven't had as much interaction with him as I would like. But they're fantastic people, so it's great to see them being recognized for all of this good work.
Okay, so time for a tricky question. So at the beginning, you kind of framed this as a foundational question about the transition between classical and quantum, right? So how large, if you like, can we make a system where it stops being quantum mechanical? So according to standard quantum mechanics, the answer to that is as large as you like, because there is no fundamental limit in standard quantum mechanics. So in order to try and understand where that limit would be, you want to be testing against some other theory, which says, no, actually, superpositions collapse at this scale, blah, blah, blah. So the question is, is there anything being tested against here? Because, for example, the things I'm aware of are things like, well, you need a superposition of a large amount of mass because we think that gravity is responsible for the collapse of the wave function. Or you need a superposition of widely separated positions because we think that that's how the collapse mechanism works. So is there a theory that was being tested against in these kind of experiments? Was there an actual sort of concrete theory that became ruled out by these experiments?
Excellent question. So short answer is no, that there wasn't a specific theory people had in mind. It was basically a question of, can we see quantum behavior even at these fairly macroscopic scales? And the answer is clearly yes. Now, in some sense, all of the quantum computing industry is banking on the fact that we don't seem to have an upper bound on the scales where quantum mechanics keeps working. Because if there is an upper bound and I start building a bigger and bigger quantum computer with more and more interacting quantum mechanical parts, at some point I may hit that bound and then it ceases to be quantum mechanical above that bound. And so this would be a catastrophic reality for quantum computing as an industry if there is in fact an upper bound. What I can say is what these experiments have shown is that there doesn't seem to be an upper bound in any like reasonable scale that we can achieve yet. Like as we improve our samples and improve our manufacturing, improve our control, we get cleaner and cleaner and cleaner quantum mechanical behavior. And this is persisting to larger and larger and larger scales. So this was just kind of the first step, what they showed. Now it's become a very kind of big industry where we keep kind of pushing that envelope and pushing that envelope to bigger and bigger scales. And as of right now, we don't really see any limit popping up, but we also don't have any theory where we're saying we expect a limit either. Now, you're right that like Penrose and other people have postulated gravity as a mechanism or other mechanisms for why there might be an upper bound. But in such circuits, it's unclear whether we can get up to those scales and say the mass of the system where that becomes relevant or not. So I'm not even sure whether these systems will be able to test those mechanisms. It would be interesting to see if we could. But something else I can addend to that is of particular interest to me is the measurement process, because very often in quantum mechanics, you have kind of this unitary quantum mechanical world where everything's in superposition, you get all these weird effects. But then I have some classical measuring device at the macroscopic scale that then measures my quantum world. And when dealing with these systems, we have to make that very precise because we need to measure these systems, which means we have to draw this distinction between what we mean by macroscopic and microscopic in order to model the measurement properly. And so it's been enlightening to me to see like how does the measurement process actually work, which is well beyond the scope of this talk, for these kind of circuits. And what we keep finding there is always an amplification step to an even more macroscopic scale where sort of collapse in this measurement process has to occur. And we can kind of see where in the circuit that has to be, at least in broad terms, but there's still no kind of clear mechanism of why this collapse occurs at those scales. So I think this is an interesting example of such a tightly controllable and macroscopic quantum system where we can start now kind of probing where is this boundary a little bit more precisely. But I think we're still pretty far away from drawing any definite conclusions about what determines that boundary.
More questions? People from Zoom? Nope. So in this case, thanks Justin again.